So how do we use these T formulae? Well, we use them to prove identities. So we can have an identity like this that looks quite tricky, and by just using those simple formulae in terms of T, we can kind of tidy them up a little bit more easily. Now, with a proof, you need to either start with the left-hand side or the right-hand side and finish with the other one. So one way to do it is to say the left-hand side equals and then work out a bunch of things that it's equal to until you get to something that it's equal to, which you'll say is the right-hand side. The other way to set out your proof is to say, look, the left-hand side equals this, which is this and this and this, and you can tidy it up to the point where you get somewhere. And it might not be the other side. You might just get to a point where you're like, okay, I'll stop there. And then you can say, look, the right-hand side is equal to, and start by listing what it is. And you might go down and down and down until you get to the same point. Okay, at that point, you can say which equals the left-hand side because you've actually already proven what the left-hand side equals over here. So this is a way of getting around it when you're not entirely sure how to jump from one part to the next, I suppose, or the jumping seems a little bit clunky. Either way is an acceptable way to set it out. And deciding which method to use is up to you, but just make sure that when you're proving an identity, you don't want to treat it like an equation and write both sides and keep doing the same thing to both sides until you get down to the point that you might say 4 equals 4 or T equals T. Instead, you need to really be specific about what the left-hand side is and what the right-hand side is and show that they are in fact the same thing. So let's start here with, we have to use the T formula. So the very first step must be to say, let's let T equal the tan of theta on 2. Now I wrote it that way because all our angles here are called theta, so I called my angle theta on 2. If these were x's, say, I'd call this x over 2. So I've got that same notation. All right, now I can use the formulas that I know for the sine of theta or the cos of theta in terms of t. So the left-hand side, which is 1 minus the cos of theta all over the sine of theta. Next, substitute in what you know for cos of theta and sine of theta in terms of t. So we have 1 minus, now cos of theta is 1 minus t squared over 1 plus t squared. And we're dividing that by 2t over 1 plus t squared. And with your setting out, you could have written, instead of this big fraction line, you could have put these in brackets and then said divided by this. On the next line, I'm going to imagine that I've done that, and then I'm going to say, hey, why don't I multiply and then flip the second fraction? But I also need to tidy up the top here. I need to give this common denominators. So if I've got 1, 1 is effectively 1 plus t squared over 1 plus t squared, isn't it? So if I have a common denominator at the top here of 1 plus t squared, then I need it to have 1 plus t squared minus, now careful here, there's no brackets, but effectively we need some brackets around that, don't we? Because I need to subtract 1 minus t squared, like that. And I need to be careful there not to make a classic sign error. Now I need to divide that whole thing by 2t over 1 plus t squared, and that's the same as multiplying it by 1 plus t squared over 2t. Now I can see that my 1 plus t squareds can cancel, so now I just need to tidy it up. On the top I've got 1 minus 1, so I get no numbers there, and I've got t squared minus t squared. That's t squared plus t squared, so it gives me 2t squared over, and on the bottom here I've just got 2t. So now I can cancel these 2's, and I can cancel one of the t's top and bottom, and then end up just with t. Now, is it easy and obvious to see that t is also equal to the right-hand side? I don't think so. So I think with this one, it makes sense to say, look, the left-hand side is t, and if I can show that the right-hand side is also t, I'll be there. So I'd be inclined to set it out this way now. I'd go over here and say the right-hand side is equal to sine of theta over 1 plus cos theta. Now let's use the same strategy. Substitute in for sine theta what that's equal to. It's 2t over 1 plus t squared. Now I need to divide by 1 plus cos of theta. This time I might do it this way. We'll write divide by like that. And we'll say 1 plus, and cos theta I know is 1 minus t squared, 1 plus t squared. You don't need to memorize these t formulae, but it's really handy if you don't have to keep looking back at your reference sheet all the time. One thing that I'm noticing all the time as I use these is that see how sine theta has 1 plus t squared as its denominator, and cos theta does as well. That actually helps me remember the formulas quite easily because I know that sine and cos are both opposite or adjacent over hypotenuse. So the fact that they've got the same denominator really, to me, makes it a little bit easier to remember what's going on. Okay, next step, we need to do 2t over 1 plus t squared and multiply it by all of this. Now, we're multiplying, we'll need to flip, but we also need to make common denominators, and it's going to be really similar to what we've done over here already. So we're going to have on the top what the denominator is, which is the 1 plus t squared, and down the bottom we're going to have what the numerator would have been when we make a common denominator. It's going to be 1 plus t squared plus 1 minus t squared. Now, we don't have the problem of the sign error here, and that's because we're adding some stuff that's complicated. So we don't really have to worry about the sign error like we do when we're subtracting some things in brackets. So we end up here with our 1 plus t squared cancelling again, and we're going to have 2t on the top, and on the bottom we've got 1 plus 1, which is 2, and we've got t squared minus t squared, so those have gone away, and now the 2's are going to cancel, and then we end up with t, which is handy because the other side was also t, so at that point we can say that that is equal to the left-hand side. Now, if you know that you're likely to get confused around here, where I did two things at once in my head, I made the common denominator and I flipped the thing upside down, go ahead and do the extra line of working. So in here, you might have had the extra line of working that would have said, all right, we've got our 2t 1 plus t squared divided by, and instead of multiplying, you could have just kept this thing the same here and said, let's make the common denominator of 1 plus t squared, and I'm going to need my 1 plus t squared here, plus 1 minus t squared. And then on the next line, when you multiply and flip this, you might want to do two things in one go there, where one of the things is easier. The tidying up of the numerator there is quite straightforward. So it's up to you how you set it out. Your working doesn't have to be exactly the same as someone else's, but it needs to be sequential enough that an examiner can follow through and see that you knew how to get from one step to the next. Now we've got a much trickier identity to prove. And this one just has a different look about it, because straight away we can see on the left-hand side, we've got sec of 2x and tan of 2x, not x. Now let's just think for a moment. What we've just been using is we've been saying, let's let t equal the tan of theta on 2, because if we know that t is equal to that, then we've got all these nice formulae for sine of theta and for cos of theta and for tan of theta in terms of t. Okay, so that's what we've learnt today. Now this looks a bit different because we've actually got the sec of 2x. So think, if we're going to use our t formulae, then what we need to do is let t equal the tan of x. All right, now why are we doing that? Well, normally we let t equal tan of theta on 2 if we want a nice neat expression for sine theta, cos theta, or tan theta. So if we want a nice neat expression for sine of 2 theta, cos of 2 theta, or tan of 2 theta, then we need to double this angle as well and let t equal the tan of theta. Okay, so notice that this angle here is half of what these ones are. All right, so I have decided here to let t equal tan of x, not x on 2, because these ones look like double-sized angles, so I've had to double this. Does that sort of make sense? All right, so sec of 2x, straight away I need to change that. The left-hand side equals 1 over the cos of 2x plus the tan of 2x. Okay, so I've just got it now so that I've got coses and I've got tans, because those are the type of formulas that I know how to use the t formula for. I've defined my t. And now that I've accounted for that, as long as this angle is half of this one, I can go ahead and generate my usual formulae with the t's in them. So I need 1 over the cos of 2x. Well, if the cos of 2x is going to be, with my t formulae, 1 minus t squared over 1 plus t squared, then if I want 1 over that, it's basically the reciprocal of it, isn't it? So two ways you could set it out. You could go straight in for your reciprocal, but let's just show every step at this point. Let's say it's 1 over 1 minus t squared, 1 plus t squared, like that. And now the tan of 2x, I need to use my tan version of the formula, which is 2t over 1 minus t squared. Okay, next step I can see that this needs to be a reciprocal, so I've got 1 plus t squared over 1 minus t squared plus 2t over 1 minus t squared. And it's convenient, we've got the common denominators here already, so we can just go ahead and add the numerators. So I've got t squared plus 2t plus 1 over 1 minus t squared. Now, you could stop there, but I can see that I can factorize this. I've got the difference of 2 squares on the bottom, and on the top, I'm thinking that this looks a lot like t plus 1 all squared. And on the bottom, I've got 1 plus t times 1 minus t. So now I can cancel a t plus 1 on the top with a t plus 1 on the bottom, and I end up with t plus 1 over 1 minus t. Obviously the t and the 1 on the top could be written around the other way if I like. All right, so I'm getting to there, and I can't easily and obviously see how that's the same as this thing here. So now I need to do the right-hand side separately and hope that it comes out as much the same thing. Okay, so the right-hand side, we have the tan of x plus pi on 4. Now, pi on 4, we must be working in radians here, and pi on 4 is 45 degrees. So now I need to use my compound angle formula for this one, because I've got the tan of two angles added together, and they're clearly not the same. So I've got the tan of x plus the tan of pi on 4 over 1 minus the tan of x multiplied by the tan of pi on 4. And that formula is on your formula sheet, so you don't have to memorize that one. Okay, what can we do next? Well, we know that the tan of 45 degrees is 1. So this gives me the tan of x plus 1. And on the bottom, I've got 1 minus tan of x times 1. So I have this. So this is looking good because I can see my finish line. I know what I need here. So if we've already said that t is the tan of x, then what I've got here is t plus 1 over 1 minus t. And that is exactly what I had there. So that equals the left-hand side. So this one looked really tricky, and I guess the hardest part of it was using our formula a different way. Instead of having t being the tan of some angle over 2 and then finding a bunch of identities that use just that angle, here we had the angle not divided by 2, and so our identities were able to have a double-sized angle.